Okay, so welcome you to the final session for this course titled Principle of Communication Systems. So today I'll basically try to cover a bit from every week's content. It's kind of a glimpse or revision over the entire course, you can say also say. So without wasting time, let us move to our first question. So this is regarding the one of the key concept from the week one, that is Parseval theorem. So we know that in the week one, basically the professor discussed about the signal in the time domain and the corresponding frequency domain representation, and how we can smoothly move between time and frequency and their crucial relations. So we see there that you have a periodic signal. So periodic signal means it repeats after a certain time. So if I want to write in terms of math here, so xt is called periodic signal when xt is equal to xt plus t, where t is called the fundamental period for x. So basically the x keeps on repeating after every t instant, and the inverse of that is called fundamental frequency.
Answer is 3.
Yes, answer is 3 only.
Yeah.
So Parseval theorem basically connects the relation between time domain and frequency domain. So you know, if the xt is a periodic signal, that can be written in this format: xt sum over k minus infinity to infinity ck a to the power j 2 pi k f naught t. By the way, f naught here is this same as the fundamental frequency, which is inverse of the fundamental period. So it basically says the time domain, this x3, this one here is the time domain representation, the same is here, but this actually says the periodic signal can be written as a summation of infinite number of sinusoids, and not at, and it doesn't have content at every frequency, it has content at frequency plus minus f naught plus minus 2 f naught, like this. So it has a non-zero discrete component at the multiples of this fundamental frequency. So that is the point. If I want to draw the frequency domain spectrum of xt here, so we can see something like that. Let's say this is the DC value or zero frequency, this is f naught, this is 2 f naught, so on, this is minus f naught, this is minus 2 f naught. So let's say it has a uh, DC component of c naught here, this one here is c minus 1, this one here is c1, this one here is c2, like that. So when it comes to the power of xt, we have already seen from the lectures, it is expressed as follows. It is actually easy for a periodic signal to define it. So basically you need to, this is px power of xt, xt square dt. So this is what power of xt is. Now I can, the Parseval theorem says I can write it in terms of its this Fourier coefficients. Those basically corresponds to Fourier spectrum. And how is it so? So this is nothing but the squared sum of all coefficients, that is the power content in these coefficients. And by the way, I have taken the interval here from minus t naught over 2 to t naught over 2. You can take it as in the question, that is 0 to t naught. Basically it would lead to the same result only, as long as you are considering interval of size t naught. So this is what Parseval theorem says. So this expression is kind of crucial. So for example, if your xt expression is a bit I would say complex, where it's difficult to compute this integral here, but you know somehow you are given the Fourier series, corresponding Fourier series or equivalent Fourier series of xt. So what you can do, if you can just take the coefficients, there would be a most likely a finite number of coefficients, and you square them and sum them up, and whatever value you obtain, that is going to be the power of that periodic signal. So the third one, as we have mentioned, is the correct answer. So we next move to the Fourier transform of a particular signal. By the way, when we talk about Fourier transform, it immediately means we are talking about some aperiodic signal. So the intuition is something like that. Let's say for a periodic signal, for a periodic signal, I'm mentioning the fundamental period as f naught. So you have a Fourier series, and it has non-zero component only at discrete frequency points, which are integer multiples of the fundamental frequency, like that. So when you talk about aperiodic signal, so what is basically aperiodic signal? That is not periodic. So aperiodic signal, you can consider a periodic signal with fundamental period infinity. Let's say if I talk about fundamental period t naught, that tends to infinity. So that is what aperiodic signal is. So when t naught tends to infinity, f naught tends to 0. So if I am try to write the Fourier series, even though it's not defined, I am uh, looking at the asymptotic case, where you are having a t naught closely approaching to infinity, that is your fundamental period closely approaching 0. So Fourier series will have non-zero components at the same intervals, right? 2 f naught and all that. But when f naught
Answer
values
is 3.
uh, of 2, yes, answer is 3 only.
Yeah. So I'm solving at my end also.
Yeah, yeah, sure, sure,
So
sure. Yeah.
fine.
So the idea something is like that. For aperiodic signal, the f naughts are going to be infinitesimally small. So at the extreme case, you will have a continuous function as a function of frequency. So this is what is Fourier transform is. So for continuous periodic signals, you have Fourier series as discussed in the previous question, and for continuous aperiodic continuous aperiodic signal, you have Fourier transform. So the question given in the slide is as follows. If I'd like to draw it, it's like this. It has a finite width 5 to minus 5 and the height of half. So we have seen the expression multiple times, but let's just do a brief calculation here. Let's say xf is a Fourier transform. Its expression is given as xt a to the power minus j 2 pi ft dt. Since actually it runs from minus infinity to infinity, but here xt is 0 outside this interval, so here our job is kind of easy. Half is a constant, so comes outside, e to the power minus j 2 pi ft dt. So we'll have 1 over minus j 2 pi f times 2 e to the power minus j 2 pi ft minus 5 to 5. So we have minus 4 pi f here, and e to the power minus j 10 pi f minus e to the power uh, j 10 pi f. So you'll see, if you calculate it, it will come out to be this, sine 10 pi f. It is just bringing these two here, and the negative sign will be cancelled out by here, because this will be actually b minus a will become a minus b, so that would lead to sine of 10 pi f, and here we will left with 1 over 2 pi f. So this is the expression of Fourier transform. If for a more general case, if I and this is okay, one more thing here. So this we can also write as 1 over 2 pi f into 10 sine 10 pi f divided by 10 pi f, and this we already know is a sinc function. So it's 10 over, sorry, it should not be here, so 1 over 2, okay, so it's 1 over 2 times 10 sinc 10 f. So if xt is a function with the value a, and its value a in the interval absolute value of t less than equal to b, its Fourier transform is going to be a times b sinc, it's 2b here, bf. So based on the interval and the amplitude, you can just directly compute what the Fourier transform is going to be. So in this case, it's half sine 10 pi f over pi f. That can be written in terms of sinc function also. So third one is the correct answer. So let us move to our next question. So it says that Gaussian pulse is given expression and its Fourier transform is denoted by GF. Fine. We have to demonstrate that the derivative of this Fourier transform with respect to the frequency is some constant times f GF. So we have supposed to find the value of alpha. So this is gt e to the power minus t square. You have to find ddf of gf, some alpha times f gf. So what is the value of alpha? So we'll see first, if we take the derivative of gt with respect to t, what we will get, dgt dt equal to minus 2t e to the power minus 3 square, and this term here is gt itself. So that means dgt dt is equal to minus 2t gt. That means tgt is equal to minus half dgt dt. So this we term as equation 1. Next we are given that gf is the Fourier transform of gt. So that means gt to the power minus 2 pi ft dt, minus infinity to infinity. So if I plan to compute derivative with respect to f here, what I am going to get, minus infinity to infinity gt, this is not a function of f, ddf of the power minus 2 pi ft dt. So we are going to obtain from here is one j should be there, minus j 2 pi t minus infinity to infinity gt to the power minus j 2 pi ft dt gf. I also know if gt is Fourier transform, we obtain gf, then the derivative will have Fourier transform uh, j 2 pi f gf. Okay, I made a slight mistake here. I cannot take the t outside because the integral is with respect to t only. So this here should be minus infinity to infinity, t would be inside. So this is basically the Fourier transform of t g t. So we have, this is equation 2 and this we call equation 3. So from this equation here we'll have Fourier transform of t gt is nothing but minus of half Fourier transform of d gt dt. And from this expression here we have that Fourier transform of t gt is nothing but 1 over j 2 pi, minus sign is there, derivative of Fourier transform dgf df is equal to times 2 is also there because these two I bring that side, Fourier transform of dgt dt. Now this I can directly plug here because Fourier transform of dgt dt, derivative of g with respect to t, is this j 2 pi f gf. So let us just plug it here by inserting a new slide. So we have minus 1 over j 2 pi dgf df times 2 is equal to Fourier transform of this is equal to j 2 pi f gf, j 2 pi f gf. So these two cancels out, minus j means minus 1 means j square, so j will go on top of that, so this will also cancel, pi will come this side, so dgf df is equal to 2 pi square f gf. So this is the final relation we have obtained. And if I look for this scalar here alpha, this alpha term is this 2 pi square. So the fourth one is the correct answer. We next move to our next question regarding the amplitude modulated signal having carrier frequency Fc and message frequency Fm. So basically you are employing an envelope detector to demodulate it with load resistance RL and capacitance C. So what is going to be desirable? Okay, so for that we need to draw the circuit of envelope detector.
Answer is 1.
uh is equal to 1 over fc. Yes, yes. So basically you are applying envelope detect the amplitude modulated signal here. The circuit is pretty simple. You have a resistance RL and you have a capacitance C here. So you are going to take the capacitance. Okay, there is a diode involved also. So just let me draw it. Um, I guess the diode should be the amplitude positive, uh, or no, this is wrong. Envelope detector diode should be on this side. So this is what your envelope detector. This is at the output. You are supposed to uh, detect the message signal. So if I want to draw it like this, so this is your AM signal is going to look like. This one you can see the rapid change is due to the carrier frequency is very high compared to your message frequency, and the message information is actually embedded into the envelope of this signal here, which corresponds to this blue line. So this actually contains the information about MT. So if I look at the amplitude modulated signal expression, it is something like this. So whenever this diode is forward biased, this capacitor is charged uh, to the V in here, that is the maximum amplitude of the M signal, and whenever this capacitor is reverse sorry whenever this diode is reverse bias, the capacitor discharges through this resistance here, so the voltage across the capacitor reduces, and this procedure keeps happening. So basically the point is the time constant of this circuit is time constant of the circuit is tau, that is given by 1 over RLC, sorry RLC only, not 1 over RLC. So it basically dictates how fast the capacitor is going to discharge or recharge. So for example, I consider for first of all, for amplitude modulated signal we know that the message frequency FM is much less than the carrier frequency. So let's say the first case, when the tau is less than 1 over FM. So what is going to happen then? That means the time constant is kind of very high. I mean that capacitor will take a lot of time to discharge. So in that case, it won't be able to follow the message signal. So when this is the scenario, capacitor discharges much slower compared to the message signal. So it will be unable to track the envelope. So this is not supposed to happen. On the other hand, if tau is much greater than the variation 1 over fc, so what will happen? The capacitor charges very fast, so it actually tracks the carrier, not envelope. So in this scenario, what will happen? The capacitor will charge and discharge very fast. So it will happen something like this. So essentially it's going to track the carrier, not the envelope itself. So these two are undesired scenario. So for that, the time constant of the circuit should be somewhere between them. Like it should be much greater than the uh, message fundamental message period here, but much smaller than the carrier 1 over carrier frequency. So this is the ideal condition. So to match this with the options, so it matches with the first one. Okay, so let us move to our next question. So it says the ordinary AM signal with modulation index and a sinusoid message signal, what is the power efficiency of the signal is? So let me just write the signal expression here for AM signal. So this one is here amplitude sensitivity, this one is message signal, this one here is carrier amplitude, and this one here is carrier frequency. So the question mentioned MT is a sinusoid message signal, so you can take it like this: AM sin 2 pi FM t. So if I consider the power of the message signal only, it's going to be AM square divided by 2. That you can compute by uh, squaring this term and integrating over one interval 0 to t fundamental period of the sin 2 pi FM t, that is 1 over Tm, and multiplying it over 1 over Tm, we'll get this m square over 2. So this signal here, if I break down, AC cos 2 pi FCT plus AC Ka mt cos 2 pi FCT. So this part here contains no information. and this part here is the one which actually carries the information. So when you talk about efficiency, this part you can consider redundant, that is it's kind of wasted, it doesn't contribute to anything. So this power is actually useful to us. So what is the power of this part? So this is again a sinusoid signal. So this has a power of AC square by 2, and this one has a power AC square K square PM by 2. So your efficiency that we are talking about is AC square K square PM by 2. PM is the power of the message signal divided by AC square by 2 plus AC square K square PM divided by 2.
The answer is 3 again.
Yes, the answer is 3 only.
Should we have to tick 3 all the time?
Yeah, that it seems happening from last year.
Yeah, fine.
So this PM here is nothing but m square by, okay, first let me just remove this part here. If we remove AC square, so we are left with K square PM divided by 1 plus K square PM. Now PM is itself m square by 2, so if we put that value here, we will get K square m square divided over 2 plus K square m square. And this Ka times am is what is called mu, that is the modulation index. So if we replace the values here, we'll just get mu square divided by 2 plus mu square. So important thing to observe, even if your modulation index is 1, which is the maximum value we can have actually, not exactly the maximum value we can have, but if we don't want any envelope distortion, then if you remember that modulation index need to be less than 1, otherwise you cannot employ envelope detection because there will be phase ambiguity. So modulation index have to be less than 1, and if it's the maximum value is 1, so even then your efficiency is only one third. So that is the main drawback of amplitude modulated signal, that in the best case scenario its power efficiency is only 33%. That is, whatever power you are employing, two-thirds of it's getting kind of wasted. So this equation anyway is important. The efficiency is always mu square plus mu square divided by 2 plus mu square. That is the third option here. So move to our next question, which is a m signal again, and with some power efficiency 1 over 9 and total power 1 over total power 1. The expression of the m signal is as follows. So you can see here also the message signal part here is sinusoidal. So if I compare with the value here, the standard expression, okay, it's already given, a plus 1 over 1 plus k sine 2 pi fm t cos 2 pi fc t. So if I the total power here, if we break it down first, AC cos 2 pi fct plus AC k sine 2 pi fm t cos 2 pi fct. So power for this is as follows: ac square by 2 plus ac square k square divided by 4. So this is given as 1. So this is our first equation. The power efficiency is ac square k square divided by 4 ac square over 2 plus ac square k square plus 4. This will become k square divided by 2 plus k square is equal to 1 over 9. This is our equation 2. So we have two unknowns ac and k, and we have two equations, so it's pretty easy to solve here. So from this equation we will have 9 k square is equal to k square plus 2. That means k square is equal to 1 over 4. That means k is equal to 1 over 2. We put this value of k here, so we'll have ac square divided by 2 1 plus k square by 2 is equal to 1. So ac square is equal to uh, 2 times k square is 1 over 4. This is 1 over 1 plus 1 over 8. So this is 8 divided by 9. So 16 over 9. Therefore AC is 4 by 3. If I plug these values, A being 4 by 3 and K being 1 over 2, we obtain this first expression here. We next move to the frequency response of the Hilbert transformer. So what basically Hilbert transformer do? So if I pass xt to Hilbert transformer,
Answer is minus. Answer is 3 again.
yes, answer is 3.
Okay, fine.
So if I denote the impulse response as ht, hf, which is the Fourier transform of it, is given as minus j sine f, where sine f basically can take two values essentially. That is one when the f is non-negative, 0 of course when f is 0, and minus 1 when f is this. So if I draw the plot here, it would be something like this. So when you multiply with minus j here, the job at a high level basically what it does, so you can see this is equal to minus j when f is positive and j when f is negative. So it's basically shift the phase, shift the positive frequency phase by minus 90, and the negative frequency is the opposite, plus 90. So that's its job. So what if I would like to find the impulse response, the time domain response? How do I obtain that? So for example, let's say I have this function sin t, which has again the same diagram. So you can see if I take the gradient of this, what it's going to be. So this part it is flat, so gradient is 0. This part it is flat, and there is a sudden jump in this here, and jump length is 2. So you can intuitively see it's a Dirac delta here. So that's what it is. At t is equal to 0, it has a non-zero gradient, and for non-zero it's just 0 because the function is flat itself. So you can see the Fourier transform of derivative of sin t is 2 only. Now we already have the Fourier transform of Hilbert transform as follows: minus j sin f. And we know from the duality property, if xt has Fourier transform xf, capital Xt will have Fourier transform of x of minus f. So how to employ that to obtain the impulse response? So let me introduce a slide here. So let's again see what are the things I have in hand right now. So I know the Fourier transform of d dt of sin t, which is 2. So if I have xt has a Fourier transform of xf, the derivative will have Fourier transform j 2 pi f xf, right?
Hello.
Hello?
Huh. Hello.
Yeah, like am I audible?
Yes, yes. Now you are audible. Earlier you were not audible.
Okay, actually I was not speaking, I was just thinking how
Okay,
to
fine, fine.
I was thinking how to get that, to use the duality property here. So and we have this Hilbert transform, that is minus j sin minus f. So accordingly you can get here 2 is equal to j 2 pi t x t. There would be another j in this side that will come from here, and the minus sign, this is not minus, will be already taken care of. Okay, so that means channel impulse response of the Hilbert transform is given as 1 over pi t. So this one here is the channel impulse response of the Hilbert transform. Just let me check whether I did it all correct or not. So it's t of xt, it should be f here. Okay, fine only. So we next have a SSB modulated signal with LSB, where xt is given as follows. So what is the Fourier transform going to be? So we are given xt is equal to mt cos 2 pi fct plus bar t sin 2 pi fct. This is the Hilbert transformed version of mt. So let me write it as follows: xt is equal to mt cos 2 pi fct plus hat t sin 2 pi fct. Cos I can write e to the power j 2 pi fct minus, sorry, plus e to the power minus j 2 pi fct divided over 2 plus m hat t e to the power j 2 pi fct minus e to the power minus j 2 pi fct divided over 2j. So if I take Fourier transform of the same, what I am going to obtain here is mf here. This one here corresponds to del f minus fc, this exponential. This one here corresponds to del f plus fc divided over 2. Then I will have Fourier transform of m hat t, which is nothing but uh,
These questions are not repeated question, right? It is not asked in the assignment. Am I right?
uh, this one, yeah, it's repeated in the assignment, I guess. This one I picked
Okay.
from there only.
All the questions?
Uh, some I changed, but some are repeated.
Fine, fine.
So Fourier transform of m hat of t is basically your product of mf with minus j sin f, and here again it's del f minus fc minus del f plus fc divided over 2j here. So what we are going to have here, this f sin of f, this j is going to cancel out. Okay, let me write again here, this mf divided by del f minus fc plus del f plus fc divided over 2 plus minus sign should be here, so minus mf sin f minus fc minus sin f plus fc. So it will be half okay. I did it wrong here, so it is m, this is m, and here it's m f minus fc sin f minus fc plus m f minus plus fc, should be minus here, sin f plus fc divided by 2. If I take f minus fc common here, so it will be 1 minus sin f minus fc plus f plus fc 1 plus sin f plus fc. So accordingly the answer is going to be f minus fc 1 minus the fourth one. So next question concerned itself with the vestigial sideband modulation and the filter HF must satisfy the constants. So I'll just briefly, very briefly tell the concept of vestigial sideband modulation. So let's say this is your message signal. After sampling, you know what you'll got. You'll get infinitely many copies of the same spectrum, and if you sample at Nyquist frequency or above, they are not overlapping. So in sideband modulation, what you essentially do, you basically pick either the lower sideband or the upper sideband to improve the efficiency, because actually both side contains the same information only, so one is actually redundant. But the issue is that ideally in mathematics you can apply a filter like this, which has a sharp cutoff uh, value, but in practice it's not achievable. So what we end up, let's say this is centered around the frequency FC, you employ a cutoff filter which has a cutoff characteristics like this. So you'll have this part, this is the vestigial part. If, for example, if you are willing to pick the lower sideband, you actually have some vestigial part of the upper sideband also, because your filter practically doesn't have this sharp kind of cutoff response. It has usually a gradual behavior like this over a finite width. So this leads to a vestigial part also being included. So that's what vestigial sideband modulation is. So if you have MF, that is your baseband signal spectrum, so basically you convert it to passband for the transmission purpose. So what you end up getting is MF minus FC and MF plus FC. Then comes your vestigial sideband, sorry, vestigial sideband modulation filter, HF. You convolute in time domain. Convolution in time domain is simple multiplication in frequency domain. So what you end up with, MF minus FC plus MF plus FC times HF, and then again you bring it to complex baseband, bring down actually, for signal processing purpose. So that will lead to this expression, MF times H F minus FC plus H F plus FC. Now for perfect reconstruction, you can see from the math here itself, this part should be equal to 1. So that is the condition that the filter for vestigial sideband modulation should satisfy. So again, this is the baseband spectrum. You convert it to passband for transmission. So after when do you sample, so you obtain this. Then you apply your filter, so obtain this. Then you have to again bring it back to the baseband for processing purpose. So this is led to this expression here. Now for perfect reconstruction, that is you want to get back MF. So this part here, it should be equal to 1. If it's less than 1, then actually you will get a like curved version of MF, which you don't want. So this equation need to be satisfied for vestigial sideband modulation, and this is the expression for that. So fourth one is the correct. Yeah, fourth one is the correct answer. So next about signal AC cos k sin 2 pi fmt. Okay, this you can see is the amplitude modulation signal only. This is passed through a square law device with output yt, and the output is passed through a band pass filter with center frequency fc. So the idea is something like that. You have xt, you are passing through a square law device which basically squares the signal component, and then you are passing through a band pass filter which has basically is going to pass the frequency component around the center frequency fc.
Answer is 4.
uh, Actually I need to calculate it. I haven't
Okay.
I don't know the answer, and I'll calculate it and I'll do that.
Because 1 and 3 are the double sideband full carrier, right?
Yeah, one is like
So it is a direct linear.
M only,
It is a
and this is
so
also
directly we can.
yes.
So, ठीक है, let's find it.
So it is just x square t. So we'll just have AC cos 2 pi fct plus k sin 2 pi fmt whole square. So we'll have AC square cos square 2 pi fct, that can directly write as cos 4 pi fct minus 1 divided by 2, or is it the other way around? 2 cos square f square t anyway plus 2 AC k cos 2 pi fct sin 2 pi fmt plus k square 1 minus cos 4 pi fmt by 2. So this is centered around 2fc. This is a DC component. This is centered around 2fm. This is again a DC component. This part here is something that is centered around fc with a bandwidth of 2fm. So this part is going to pass through this band pass filter. So yes, as you pointed out that 4 is the answer only. Actually the question is made a bit easier by mentioning that DSBSC part here, because all three have this carrier component. So this is a quadrature carrier multiplexing signal. So what should be the complex envelope corresponds to this signal? So this is given as cos 2000 pi t. This is the signal part, and cos 10,000 10 to the power 5 pi t. This is the carrier part, plus sine 2000 pi t sine 10 to the power 5 pi t. So standard QCM expression is as follows. We have a in phase part and we have this carrier, and quadrature part, functions of t, with again the carrier. So comparing, we get that in phase part is cos 2000 pi t, quadrature part is minus sine 2000 pi t. So what is going to be the complex envelope? Okay, the complex envelope expression for QCM is given as follows: xi plus j x q t. This is also the complex baseband equivalent of QCM, and it is given as cos 2000 pi t minus j sine 2000 pi t. So this we can write as cos minus 2000 pi t, because cos of minus x and cos of x are same values, and this minus we can take inside because sine of x is sine of minus x, 2000 pi t. So this is nothing but the exponential minus j 2000 pi t. So the complex envelope expression is given as follows. The complex pre-envelope, by the way, it's given as xit plus jxqt e to the power j 2 pi fct. That is basically a passband equivalent, but since we are asked about complex envelope, which is nothing but the baseband equivalent of QCM, the second one is the answer. Okay, so we have to find here now the passband signal sine 5000 pi t. Okay, sine 5000 pi t. let's call it xt, and if I pass through Hilbert transformer, I'll get minus cos 5000 pi t.
Hello.
Hello.
Okay. You are not audible.
Hello, am I audible now?
Yes, yes.
Okay, okay. So my complex pre-envelope for this passband signal is going to be xt plus j x hat t. This is x hat t, what we obtain by applying Hilbert transform over the passband signal. So this is sine 5000 pi t plus, sorry, minus j cos 5000 pi t. Now this can be written as sine of x is equal to cos pi by 2 minus x. So cos pi by 2 minus 5000 pi t. Similarly, this can be written as sine pi by 2 minus 5000 pi t. Now this minus sign need to be taken inside to convert it to a exponential sinusoid. So this we do first. J sine 5000 pi t minus pi by 2. For cos it will remain the same because cos of minus x is equal to cos x again. So this is nothing but the exponential to the power j 2 pi, sorry, there is no 2 pi here, just a moment, e to the power j 5000 pi t minus pi over 2 or e to the power j pi 5000 t minus 1 over 2. So this is the complex pre-envelope for the passband signal. You'll have the passband signal, you pass through a Hilbert transformer, you obtain the Hilbert transform version of that x hat of t. Your complex pre-envelope is going to be passband signal plus it Hilbert transformed version, j times Hilbert transform version, sorry. And then you have to see what the term is, like do some maths and bring it in a standard form. Like for example, here it's exponential sinusoid, in a question it might be something else. The second one is the correct answer. Next we talk about the phase modulated signal. We have AC cos 2 pi fct, sorry, plus kp am sin 2 pi fmt. First of all, the modulation index is defined as maximum frequency deviation divided by maximum frequency content of the message. Now from this expression we can see the instantaneous phase is given as this: 2 pi fct plus kp am sine 2 pi fm t. So instantaneous phase is going to be ddt theta it 1 over 2 pi. So when you do that, you will obtain fc plus kp am fm. So the maximum frequency deviation, okay, it should be sine 2 pi fm t. Maximum frequency deviation is equal to fit, sorry, max of fit minus carrier frequency, and this will happen when this term will go to 1. So you can see this term will go to 1, your maximum frequency deviation is going to be kp am fm. So according to this formula here, let's say your modulation index you are denoting as mu. So your mu here is del f, this we call as del f, the frequency deviation, divided by fm is the maximum frequency content of the message. So here del f we found as kp am fm divided by fm. So for phase modulated signal, your modulation index is going to be kp times am. That is the fourth one. So next we have a frequency modulated signal with carrier frequency this and described by this expression. Okay, so what is the maximum frequency deviation? Del f. So our frequency modulated signal is given as this: phi t is equal to 10 cos 2 pi fct plus 6 times cos 2000 pi t. Here fc is given as 3 into 10 to the power 8. So instantaneous phase theta it is given as 2 pi fct plus 6 times cos 2000 pi t. Now your instantaneous frequency fit is going to be 1 over 2 pi d theta it dt, that is fc plus 12 into 10 to the power 3 cos sorry, it will be divided by 2 pi here. So 12 into 10 to the power 3 pi divided by 2 pi cos 2000 pi t. So that means fc plus 6 into 10 to the power 3 cos 2000 pi t. So this is going to be the instantaneous frequency expression. So the maximum frequency deviation del f is equal to max of fit minus fc, that is 6 into 10 to the power 3 hertz or 6 kilohertz. The second option is the correct one. Next we look at the frequency modulated signal again, and this question asks about the approximate bandwidth calculated using Carson's rule. Carson's rule is kind of important, so let me write the question first. 4 pi into 10 to the power 60 plus 2 sine 4 into 10 to the power 3 pi t. So according to Carson's rule, there are a lot of calculation involved actually to find the bandwidth of a frequency modulated signal using zeroth order Bessel function that we have already covered in one of the previous assignment session, if I remember correctly. Now I'll just give you the formula, which is important of course for the exam. According to the Carson's rule, bandwidth for frequency modulated signal is given as 2 times 1 plus 1 over beta del f, or you can write it in this way, 1 plus beta fm. So you can see from this expression, when the modulation index, okay, first of all this beta is modulation index, which is given as del f by fm. So when beta is much greater than 1, you can see this one will approximately becomes 2 times maximum frequency deviation, and when beta modulation index is much less than 1, so you can see this approximately equal to twice the maximum frequency content of the message signal. So let us see in our case which one of these hold. So we have again the instantaneous phase as 4 pi into 10 to the power 6t plus 2 sine 4 into 10 to the power 3 pi t. So fm, you can see here from this expression, your fm is 2 times 10 to the power 3 hertz. Now the instantaneous phase is obtained as 1 over 2 pi ddt of theta I t, which is 2 times 10 to the power 6 plus 4 into 10 to the power 3 sine 4 into 10 to the power 3 pi t. So from this expression we can see the maximum frequency deviation is 4 into 10 to the power 3. So that means our beta is 4 into 10 to the power 3 divided by 2 into 10 to the power 3, that is 2 here. So it's neither much greater than 1 nor much less than 1, so we have to use any of this equation. So let's use the second one, that is 2 times 1 plus beta times fm, that is 2 times 1 plus beta is 3 into fm is 2 into 10 to the power 3, that is 12 kilohertz. So first one is the correct option in this case. But in the actual question, one of the situation might arise when your modulation index is much greater than 1 or much less than 1, then you will find your approximate bandwidth for modulation index much greater than 1 is twice the maximum frequency deviation, and for modulation index much less than 1, the bandwidth is nothing but twice the maximum frequency content of the message signal. So we have a band limited signal which is being sampled at a rate greater than the Nyquist rate. So what is the original signal reconstructed from the samples via interpolation using which one of these pulses? So whenever I say the band limited signal sampled at the rate greater than Nyquist rate, I can immediately see what's happening. So this is, let's say, the spectrum of the signal. If we sample at a rate greater than Nyquist rate, we will obtain something like this: non-overlapping copies. This is 0, this is at fc, this is fc minus fm, this is fm, and there is a gap between them. So if I talk about the sampled signal, that is m delta t, it's given as m nts delta t minus nts. Ts is, by the way, the sampling period, and n runs from minus infinity to infinity. So this is what my sample signal is. So original signal reconstruction, you are going to pass this thing to a low pass filter, right? You're going to pass it through a low pass filter, which is basically characteristics like this, centered around the baseband. So it will only through this component pass, and then you can perfectly reconstruct your signal as it was being sent. So this low pass filter, this is the frequency domain representation. So the filter response of low pass filter is given as sinc function. If you remember correctly, this rectangular pulse, if you have a rectangular pulse in frequency domain, you will have a sinc function in time domain. If you have a rectangular pulse in time domain, the frequency domain representation is a sinc pulse. So this is the filter response is going to be. So when I say that I am passing this through a low pass filter and obtaining this is all happening in the frequency domain. What is the time domain representation is going to be? So time domain, this is going to happen. So this is going to convolve with the filter response ht. So this will result into this n is equal to minus infinity to infinity m nts h t convolved with del deduct delta train. So this one is a scalar, so it doesn't have any impact in the convolution operation. So we are going to obtain this n is equal to minus infinity to infinity m nts h t minus nts. N is equal to minus infinity infinity m nts. I'll just go one more step. Sinc ft, it's fst minus n, because fsts is going to be 1. So you can see this is nothing but a scaled, this is the scaling factor scaled summation of sinc pulses. So that is how you interpolate to recover the signal being transmitted. So let's say this is the sinc pulse at n is equal to 0. This one is the sinc pulse at n is equal to 1. This is the sinc pulse at minus 1. This is at n is equal to 0, this is at n is equal to 1, this is at n is equal to minus 1, like that. So the original signal, this one which is happening in the frequency domain, actually how it's happening, this is reconstructed from these samples means these ones, message samples at integer multiples of sampling period via interpolation using the sinc pulses. So this is determined by the low pass filter here. Low pass filter has a rectangular pulse uh, in the frequency spectrum. So the time domain response is going to be a sinc pulse, and you use this sinc pulse to interpolate the original, to reconstruct the original signal. And this is how it's being happening. So this is your reconstructed signal. This is m reconstructed mt. So let us move to this now next question, which basically asks about you are having a parallel resonant LC circuit whose capacitance is varying according to the message signal. So what is the approximate carrier frequency of the resulting frequency modulated signal xt? Okay, so it's actually pretty straightforward, even if the question looks a bit so the carrier frequency is going to be the resonant frequency of this LC circuit, which is given by Fc is equal to 1 over 2 pi root over LC. So this is being computed at 2 pi. LC is 10 to the power what is that, 10 to the power minus 3, and capacitor is 50 into 10 to the power minus 6 minus 10 to the power minus 7 mt. So if I take a common here of 10 to the power minus 7, so this will become 10 to the power minus 10, and this will become 15 10 to the power 10 to the power minus 7 5, okay, sorry, 500 minus mt. So this will become 10 to the power 5 divided by 2 pi square root of 500 minus mt. Now you see that mt's maximum amplitude is mentioned is much less than 1, so we see that square root of 1 minus x can be approximated as 1 minus x to the power, okay, this is equal to 1 minus x to the power minus half, and this can be approximated as 1 plus x by 2 for x much less than 1. So we apply the same here, 10 to the power 5 divided by 2 pi times 500 plus 1 over 2 mt. So this is going to be okay, did I do something wrong here? Mt is approximate carrier frequency 50 microfarad. So this part will anyway insignificant, so we can consider it approximately 0. It's a 10 to the power the circuit message varying, okay, 10 to the power 5 into 500 divided by 2 pi. It's 10 to the power 5 10 to the power minus 7 here, 10 to the power minus 9 4. Okay, I did this mistake here, sorry about that. 500 is going to be here only, and I will have this is square root of 500. I'll have 1 over 1000 here. This is 1, and the square root of 500 times 1 minus mt divided by 500. Okay, now it's fine. So this is going to be a 10 to the power 4 divided by 2 pi into square root of 5. So let me just calculate it. 4 10 divided by 5 square root divided by 2 divided by pi. It's 711.76 hertz. So this second option is the correct one here. So this is the concept about the delta modulation, where instead of quantizing the samples, you remember we quantize the difference between consecutive samples, and since all the natural signals are, you can see they are highly correlated, like from one sample to another sample the things doesn't change much, so the difference is also going to be very small. So when you actually quantize the difference, you will have uh, you will need less bit for a given resolution, so you can this you can get rid of this like this what is that, computational complexity. You don't need a lot of number of bits to quantize your symbols, since you are quantizing the only the difference, and since the difference is very small, you can obtain finer resolution. So if you remember, we have already discussed that in delta modulation, which distortion occur when signal rises or falls slowly in comparison to the reconstructed signal. So for example, if delta modulation, the idea is that I have a signal of this sort increasing or decreasing like that, and I am trying to have a staircase approximation for the same, like this. So basically I am trying to quantize the difference between each symbols, and that's how I track the signal envelope. Now the issue is when the signal itself rise or fall very slowly. For example, you can see here the signal is almost kind of flat, or the rate of increase and decrease is very low, and when you actually use the large step size in the reconstructed signal, what is going to happen in this case? For example, here you are having this kind of tracking, so you can see this large step size will lead to a large error also, so that we call granular noise. That is known as granular noise here. Granular noise arises when signal variation is less and step size, by step size I mean the for quantization step size is large. The opposite thing happen when the signal rises very fast and your step size is very slow. So then in the case you can see, like here you can see the difference. Signal changes very fast and step size is small. Then we have large reconstruction error. You can see there is a huge gap between the original signal and the reconstructed signal. So this is known as slope overload distortion, and this happens when the opposite of the thing what is mentioned in the question says signal rises or falls slowly, then you lead to granular noise. But when signal rises or falls very fast comparison to the reconstructed signal, then you will have slope overload distortion. So you next move to our question which concerned with the time division multiplexing. You have already seen where we can actually multiplex a large number of signals and transmit is over the same time frequency resources. So how we can achieve that is via commutator. Let's say this is signal 1, this is signal 2, like up to signal n. So we have a commutator here which goes from here to here and here to there. There you have here the all the reconstructed signal. For example, you have m1, you have m2 up to mn. So you have a signal from m1 ts, a signal from m2 ts up to mn ts. So this is a time division multiplexing. Time division multiplexing. So basically here the sampling operation uses flat top sample with 2 microsecond duration, and multiplexing operation includes provision for synchronization by adding an extra pulse of sufficient amplitude and also 2 microsecond duration. The highest frequency component of voice signal is 3 kilohertz. So highest frequency is 3 kilohertz. So you are sampling frequency, you are sampling at Nyquist rate, so it's 6 kilohertz, and at 6 kilohertz you are sampling 20 voice signals, right? So your sampling frequency is 20 kilohertz, so your sampling time is 166.67 microsecond. So what is the approximate silence time between successive pulse of the multiplex signals? We have 20 voice signals here and one extra pulse, that is 21. So you have total 21 signals. So for each signal, the time you have is 166.67 divided by 21, that is given as, just calculate, 166.67 divided by 21, that is 7.936 microsecond. Now each the sampling is not using Dirac delta function, these are using flat top samples, not Dirac delta samples, and this flat top samples has 2 microsecond duration. So the silence period is going to be, for each sample you have 7.93 microsecond, and each sample has a duration of 2 microsecond. Sample duration, so your silence time between successive pulse is going to be 5.936 microsecond. That is the third option here. So this is regarding the concept of a superheader, the frequency mixing task. So it basically says you have incoming signal mt cos 2 pi fct, but this has a very high carrier frequency. The processing is kind of very expensive there, and computationally complex also. So what we do, we basically multiplex with a local oscillator here, local oscillator generated sinusoid, that is, let's say, of duration cos 2 pi fc plus f if t.
Answer
So
is 1.
so it's a broadcast frequency of 1 kilohertz, intermediate is 500 hertz, fine. So that is your local oscillator has a frequency of 1.5, and that is twice the times of to yes, answer is 1. So this would lead to a sinusoid here of frequency 2 pi IFT, intermediate frequency, and we can do the processing here. Since it's a super heterodyne receiver, the local oscillator frequency must be higher than the frequency of the signal being transmitted. That is, the broadcast frequency is 1 kilohertz. So the local oscillator has frequency FC plus FIF, that is 1.5 kilohertz. 1.5 kilohertz. But the issue is, this is not the only signal that would produce a frequency of intermediately FIF. There is another one which is FC plus FIF, sorry, FC plus 2 FIF. So if you mix with the sinusoid produced by the local oscillator, you will also have a component of cos 2 pi FIF, and that is the issue. So this is what is unwanted frequency, and this is termed as image frequency. And image frequency value is the broadcast frequency plus twice the intermediate frequency. So broadcast here is 1 kilohertz, intermediate is 0.5 kilohertz, so it's 2 times 0.5, so that is a 2 kilohertz. So 2 kilohertz is going to cause unwanted interference to this signal unless you have some pre-filtering kind of before this operation of multiplying with the sinusoid generated by the local oscillator. So this is about a uniform quantizer with 120 quantization levels, and
Sir,
this
how
is
many questions are still remaining?
uh, there are maybe 4 5, but maybe
Fine, fine.
I'll answer, maybe I'll do 3 4 of them and we can conclude the session, because the rest of the those are very recent ones, like from the week 10 11 and 12, so these are kind of fresh only, so I guess.
No, just you just complete the all. Will recall your recorded video in that case.
Okay, okay, sure, sure.
Mm.
So this one I'm just directly writing the frequency here. So quantization noise power, quantization noise power, if you remember the formula, it's minus 10 log base 10 3 plus 20 log base 10 maximum message amplitude plus 6 B, where the B is the number of bits required to represent the quantization. So you have 128 quantization level, so 128 is equal to 2 to the power 7. So basically we need 7 bits, and maximum message amplitude is 1000. So let us just put the values: 10 log base 10 3 plus 20 log base 10 10 to the power 3 plus 6 times 7. Okay, this one here is minus, sorry. So we are going to have 10 log base 10 3, just let me do that. 3, it's 4.77 minus plus, this is 3, so it's 60 minus 6 42. So 60 minus 46.77, so it's 33.23 dB. So the quantization noise power in this particular case is going to be 13.23 dB. Next we talk about the conditional probability P of A given B. This we can directly write the formula of that. This is the division bit in the numerator. You have probability of A intersection of B and given by P over B. One corollary could be when A and B are independent, when actually A and B are independent, your probability, conditional probability of A given B is probability of A, because since they are independent, the occurrence of B doesn't impact the occurrence of A. So in that case you will have probability of A intersection B as the product of the individual events. Now probability of A union B. So this can be most efficiently done by visualizing it. So this is the, let's say this is A and this is B. So there are three regions you can see which are non-overlapping with each other. I am marking them with different color. So this one here is probability of, sorry, not probability will not be included. This one here is the uh, A union with, sorry, not union, this one here is the A intersection with B bar, A and whatever not in B. This one here is the intersection with A and B, and this third one is A bar intersection with B. So these three are non-overlapping, so the probability of this set is the sum of the probability of these non-overlapping sets, which corresponds to this case, the third one. No, sorry, not the third one, second one. So this is about a 4-array PAM constellation with different probabilities given, and A is this set and B is this. What is the probability? So first I need to compute the probabilities. So P of alpha, P of minus 3 alpha plus P of minus alpha plus P of 3 alpha is equal to 1. So this is 4 P of minus 3 alpha plus P of minus 3 alpha. This is 2 P of minus 3 alpha plus 2 P of minus 3 alpha again. So probability of minus 3 alpha is 5 to 7, 1 over 9. So probability of alpha is 4 over 9, and probability of minus alpha and probability of 3 alpha each are 2 over 9. So A is the event 3 alpha and alpha, and B is the event minus alpha. So probability of B given A, probability of B given A should be probability of A union B divided by probability of A. But here I guess this should not be a minus here, otherwise there would be no common thing, so it would just be 0. So A intersection B is going to be alpha only, and probability of A is nothing but probability of 3 alpha plus probability of alpha. So that is 6 over 9, and probability of uh, this thing is probability of A intersection B is probability of alpha is 4 over 9. This is 4 over 9 by 6 over 9, so that is 2 over 3. So the first one is the correct one.
It is, I think, similar, right?
Yes, 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 this is similar only. So that's what
Fine.
I'm.
But just go through the questions once. Rest of the question.
Okay. This is regarding that again optimal quantization level, which we have discussed in the, I guess, previous to previous session.
Okay.
And this one is that
Fine.
binary
After,
symmetric
after.
channel. We have seen it
Fine.
multiple times, and
Yes.
this is also same only.
Fine.
And yeah. So I guess I plan to skip these things. I just added them in case I required more time. I would have discussed. Otherwise, it's the same only. Actually, I plan to conclude here
So what
because
about this random process X is Gaussian if
okay.
the answer is?
Yeah, this is for when the joint probability density function of x t1 t2 up to tn for any choice of t1 and any n, it should be Gaussian.
So it is 3, right?
Yes, it is the third one. So it's not that I pick some specific T1 and Tn and for that case it turns out to be Gaussian. That doesn't make the process Gaussian. It should hold for any choice of T and any number of these Tn variables. If they hold for all case it's jointly Gaussian, then only the random process is called to be Gaussian only.
Fine. Fine.
Third option. Yeah.
Okay. So you can just provide the solution. Rest of the four, if you're not going to solve right now.
Okay. 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 I'll
So when you upload the,
okay. I'll upload that
or you
solution.
just continue the lecture. I'm just leaving right now.
Okay.
So
Yeah,
fine.
like
Fine.
actually I have some TA
Work
duty
to do.
also after that. Yeah, so
Fine.
I'll
Fine.
just go. But I will upload
Fine.
the
Fine.
solutions in the
Fine.
drive for all of them.
Thank you so much.
Yeah.
Thank you. Have a
Yeah.
nice day.
Thank you. Thank you.